Thanks, Franco, very much for the introduction. And I can say, to use the words of Professor Whitesides yesterday, as a new assistant professor who might be somewhat optically transparent, wow. So I thank you very much for the opportunity to be here, and it's a pleasure to have a chance to partake in celebrating the life and work of Dr. Khurana. So thank you. I'm going to shift gears a little bit, again, in the sense that I'm in the mechanical engineering department, quite literally, but also in that this work was done while I was a postdoc at IBM Almaden Research Center. I'll say up front that IBM did and still intends at some point to use this technology to make computer chips, whether that's 10 years down the road or 50, I don't know, but it is certainly very promising. I'm going to define a very different top-down here. Top-down in the sense of traditional silicon nanofabrication. And of course, the bottom-up is the self-assembly of DNA nanostructures, in this case, DNA origami. I'll also talk about recent work in my lab done by Robon Han, who is trying to identify the mechanisms that are responsible for why origami absorbs the surfaces, which I'll now get into. And of course, this was a huge collaboration with Paul Rodemund, who invented the DNA origami technique. So for motivation, I'm not going to talk about Moore's Law, but I do want to just give you a sense of where the semiconductor industry thinks it's going in the next 10 or 15 or so years. And this is the very well-known international technology roadmap for semiconductors that everyone in the industry follows. It identifies feature sizes, if you will, that are necessary to keep the engine of economic development going that results in shrinking the size of the transistors in your computer chips. In this case, this is DRAM memory. And these are the nodes currently under development. Actually, we're now here close to the 32 nanometer node, and these are the technologies that are projected that will need to be developed or are currently under development to make this happen. And you'll see down here directed self-assembly. You'll also see that this chart only goes out to 16 nanometers 10 years from now. And so, of course, we've already seen that DNA provides a means for making much smaller nanostructures, arguably an order of magnitude smaller. And so that's where I begin my talk. The semiconductor industry has also embraced the fact that eventually they're going to have to move away from traditional fabrication methods and get to the assembly of nanowires, nanotubes, and fullerenes, which has been a hot topic for many, many years. In the last few years, this field has exploded with applications that actually find ways of assembling these nanowires, nanotubes, and fullerenes into two-dimensional architectures. Still not three-dimensional, but this is the future of semiconductor manufacturing. The question is, how do we get there? And how do we actually improve mechanisms for assembly beyond this 16 nanometer node? And so here's the answer, which I don't need to tell you about. Of course, from pioneering work from the founder of this field, Ned Seaman, and then from two-dimensional to three-dimensional structures, and then the ability to assemble these tiles, if you will, or rafts into very large areas, and then to image them very precisely. Great work from the Winfrey group. And then I'll show you deposition of this particular structure, which by comparison is extremely simple, but it represented at the time that we started doing this work the state of the art in what you could put down on a surface controllably. And so that leads us to DNA origami. This is actually what we're going to place on our surface. And again, I don't have to give you an introduction of this, but suffice it to say that, again, by cleverly designing these two-dimensional structures, again, in each beaker, you develop each of these individual molecules. So here's the design, and then, of course, this is what it looks like with an AFM image, and you can image many of these over large areas. But in fact, one of the fundamental limitations, if you will, is that these are randomly dispersed. They go down on a surface, and you sort of let the chips fall, and that's where these structures end up. So we'd really like to have a way to integrate these bottom-up structures with traditional semiconductor fabrication. But one of the other advantages of DNA origami in general, and really the power of DNA nanotechnology, is the ability to address individual pixels. So Paul demonstrated that you can create extra loops at these sites, the so-called nano breadboard. The term was not coined by him, but producing arrays onto which you could potentially assemble other objects. And in fact, those applications have been demonstrated very recently. But if you think about this as a nano breadboard and you think about the resolution here on the order of about 6 nanometers, again, that's at least 20 or 30 years ahead of where the semiconductor industry is at that 16 nanometer node. So going back to my first introductory slide, this is where IBM wanted to go with this work. And this is how we propose to do it. So this is merging top-down. Again, the top-down is these templates fabricated by traditional semiconductor manufacturing. In this case, this could be done by optical lithography. It could be done by electron beam lithography, by a range of technologies that already exist. You assemble your DNA nanostructure in a beaker. You then assemble the DNA pattern onto this template, and that's the step that I'll talk about. And then eventually, and this work again has been demonstrated and will come out very soon by Jen Cha when she was at IBM, had taken it to the next step, as have many other people, to assemble components or nano components on these nano breadboards. And so that's step 4, which I won't talk about. But focusing here, there are some requirements for integrating these biological nanostructures into the semiconductor world. So the first thing is that we're not going to retool, the Intels and the AMDs of the world are not going to retool their billions of dollar fabs and suddenly start making computer chips out of biological molecules. So we have to come up with a way of placing these biomolecules that have nanoscale features, but it has to be compatible with existing processes if we're going to have any hope of doing this in the near future. But what hadn't been demonstrated prior to this work here is the ability to place objects selectively, particularly to control position and also to control rotation. And that'll make more sense in a few slides. Of course, we also want a very high yield. We want yields that are appropriate for the semiconductor industry. That is to say, 100%, which is a big goal. It's a big task to try and accomplish, but we're certainly up to the challenge. And then eventually, we'd use these for scaffolds to assemble other components. So surface placement of DNA is not new by any means. Our own Dave Schwartz, some of the early work in 1981, so-called combing of DNA, in this case double-strand DNA, and also the rafts that I showed you briefly from Meyer Lieberman's group, the ability to place these rafts on protonated silicon aptes surfaces, so functionalized surfaces where you can put down these molecules in a very specific way. This is additional work slightly earlier from Seaman and Alvasados than the work he presented, but this is a very elegant means, one of the earlier demonstrations of placing nanoparticles, in this case, on these assembled arrays of tiles. But the interesting thing here is that there's a whole range of interactions that we can tweak. There's choice of DNA, sticky ends, blunt ends, no ends. There's a variety of surface interactions, and maybe instead of a plus, this should really be a times, because the combination of these choices and these choices for how DNA interacts with surfaces leads to an extremely complex problem. So we broke it down into something very simple. We started with a technique that was well developed. So we're using a template layer that is fabricated on a semiconductor-compatible surface, SiO2 or just silicon. We in one case, put down a template layer of diamond-like carbon, glassy amorphous carbon. And on top of that, we put a photoresist, which we then use e-beam lithography to pattern, develop, leave these features. And then this is a key step for both template layers. I should say there were 2 types of templates. There was either diamond-like carbon or there was a tetramethylsilyl on top of SiO2, originally in the form of HMDS. And after development, this plasma step activates the surface at these specific sites, producing sites when you strip away the resist for origami to bind to. And I showed you a range of structures. The triangle structure might stick out. That's what we started working with. This triangle, of course, the origami is going to go to this specific site. That's the goal. That's what we're going towards. But we have a lot of flexibility, just that e-beam technology provides, that e-beam lithography affords. We can make arbitrary shapes, so lines, polygons, on the order of about 50 or so nanometers. Again, the scale is quite large because we're pushing the limits of lithography, but that doesn't matter because the origami itself is on the order of 100 nanometers, so it's something that we can actually position. So we have a good match of the two size scales. We can control the sidewalls, we can control pitch, shape, and depth, and of course we learn a lot as we go through this process and we see what works and what doesn't. So here's a pattern, here's what it looks like. That's the template for assembling origami, and then there's an AFM scan of what the bumps look like after etching down through to create these sites for absorption. And this is just a simple cartoon. We use atomic force microscopy as the means for essentially both depositing the origami. The origami goes down in a self-assembling way. It's in a drop of solution. It will naturally find its position in a lock and key type mechanism, but we're continuously scanning as we do this so that we can see where the origami goes. Of course, that begs the question, what's wrong with scanning? Well, you presumably are knocking off origami as it's going into the surface, into these template sites. And it turns out that the surface is extremely sensitive in terms of the surface chemistry and the interaction, which I'll get to in a few slides. A couple other variables include, of course, imaging conditions. We optimize to minimize this deleterious interaction. And then also that the concentration affects the absorption rate. And here's the first demonstration of what we can do using stripes that we've E-beam patterned. You can put down origami where you want to, so you have positional control for the most part. You don't have rotational control because, again, the features are the wrong size. But you can place these structures at specific points. So if you show this to a lithographer, they'll laugh at you. But the next step was to take this to specific sites that bind origami that is of a specific shape. What I didn't tell you in the previous slide is that it's extremely sensitive to ionic strength, which turns out to be a huge variable that we can tune. Again, that's the second half of the talk here. So we start in tris acetate EDTA buffer. Origami is formed at a somewhat low concentration, well, a normal concentration of magnesium chloride. Turns out that at that concentration, this was an attempt at depositing origami on this surface. Nothing happens. So we have to actually increase that concentration tenfold. I'll show you the good results in a second, but another bad result is if we increase it way too high, at 1 molar, almost unheard of in terms of salt concentration. Origami goes down very selectively and very poorly. It still stays together, which is remarkable. It still goes to the surface, but of course that's far less than the yield that we need to see. But if we get right in between, just a tenfold increase over the ion concentration where this origami is formed, we can see about 95% filling of these sites. We have up-down triangles, and we have reasonably good rotation control. So here is some statistics on how good the rotation control is. So here's down and up triangles in red and blue, and you can plot a histogram of where they fall and what the angular variation is. It turns out for diamond-like carbon, it's about plus or minus 10 degrees. Again, it's good presenting this to a group of biologists and biochemists because you look at this and you say, wow, that looks pretty good. Well, you know, it's not quite good enough for the semiconductor industry at this point, so there's a lot of room to go. But it's certainly a step in the right direction. So I also want to talk about this sort of sweet spot for ionic strength and concentration of magnesium chloride. Well, it turns out that the absorption of origami is extremely dependent on that ionic strength. You can tune it. And so this is a movie, if you will, of scans, AFM scans separated by about 2 minutes, where we're changing the size of the sites, so going from small to very big. And you can see that down here where the site is smaller than the size of the origami itself, origami isn't likely to stay at this site. But if you look at some of these sites in the middle, the origami is much more likely to stay there in time over the full course of this movie. And so we're just there. We're right there at equilibrium. You can see some partial origami that is either knocked out by the tip or partially imaged. It's not origami that's not well formed. It's simply that it sticks to the surface, the tip comes by and knocks it off. And then we differentiated between triangles and rectangles. And one thing we found immediately is that rectangles are a little bit more difficult to image in that the binding is not as strong. But of course, there's no orientational control afforded by this rectangular structure. So in the case of triangles, it's easy to fit a triangle to a triangle, and you know which way it goes. With a rectangle, you've got a twofold symmetry. So we took this another step forward, and this is work I'd really like to push here at Wisconsin, is to find ways for not just producing a single site and putting origami down at that one place, but for assembling multiple origami over sites that are much larger. So we played around with this idea of making these geometric shapes composed of 1, 2, 3, and on up. Sites that fit that many pieces of origami. And you can see that when we tweak the ionic strength and get the size correct, you have 1-to-1 the triangles that I showed you before, but you can see in the parallelograms we've got pretty good registration of these 2 features, and then we've got, the trapezoid, and then the parallelogram we've got 3, and then on up to the triangles, 4 origami up to hexagons of 6. So this, I think, is very interesting. It, again, seems to be very sensitive to ionic strength. Thank you. So the fundamental question here is, what role does ionic strength play in absorption of origami? And that's what we started with, my student Robin Han here at UW, to try to answer this question. And so I went back to sort of my bread and butter as a surface chemist, as a material scientist, in that dielectric particles and surfaces acquire a charge due to absorption of potential determining ions. This is very well described in the case of double-strand DNA, as is this ion bridge model for how DNA presumably absorbs to a charged surface. So it's mediated by this charge interaction between a divalent cation. And in fact, we find that the concentration of divalent cation is very important. There's other ions in solution, including monovalent cations, including just hydrogen ion that we can tune through pH. We can actually measure what's happening on the surface by looking at this parameter known as the Zeta potential, which is essentially a representation of surface charge. But before we do that, we note that the magnesium concentration, which we can tune independently, and the sodium concentration, when you put them together, there's a competition, if you will, between these 2 ions that really dictates how well this origami absorbs. And so the 2 cases that I show here, these are the absorption points. That is, the origami likes to absorb very well over a broad range of sodium concentration at a single magnesium concentration. And so here we have somewhat decreasing densities, but we're still absorbing origami. If we do the same thing at a slightly lower concentration, we get to what are called these transition points, where the density gets much lower. So just the ability to tune between magnesium and sodium concentration is extremely important. And we'd like to be able to measure that, again, using this streaming current technique. So this is a means of measuring electrokinetic surface charge density. It should tell us something about the way origami absorbs. And we do that using this technique that's analogous essentially to electrophoresis, except in this case we're flowing through solution and measuring a current. So it's sort of the analog. And these are the results as a function of pH and ionic strength. One of the very surprising things is down here and we started with Mica, I should say, which is a surface that we know very well, as opposed to SiO2. So one of the surprising things is that there's a big dependence on pH. As we get up into low hydrogen ion concentration, the magnesium takes over. We get a phenomenon known as charge inversion, where the surface is flooded with magnesium charge. And if we do that as a function of ionic strength, we see that the Zeta potential, and therefore the effective electrokinetic surface charge density, is extremely different. So way down here at low concentrations, we have a low percentage of magnesium absorbed. And then up here at high pH, in this case, the magnesium pushes the hydrogen away, and we have magnesium flooding the surface. And so we can calculate what we think is a critical surface charge density where this cutoff occurs. And so we took this a step further. We have the ability to tune ionic strength. How about pH? We should be able to do the same thing. And so here we did a simple experiment where we have origami. We put it at a concentration where it's happy, a relatively low concentration of magnesium chloride, but it likes being there on mica. And then we took it up to a pH, added a pH with sodium chloride where we wouldn't expect origami to stay, at least according to the results at a low pH. In fact, we see, based on the Zeta potential results, that this actually works. We can actually get this to stay. Just 1 or 2 more slides. we can get the origami to stay in this case. And then when we go back down to pH 8 at the same salt concentrations, the origami goes away. So there's clearly the ability to tune both ionic strength and pH. That's something we're continuing to explore. And then the difference between silica and mica is particularly pronounced. It's a dramatically different behavior here on SiO2, which is the surface, again, that was relevant to the semiconductor industry. We can measure these charge densities, and we can see that the charge densities are also very different. So there is a very narrow range here on mica and on SiO2. Of course, on mica, origami absorbs at all these ionic strengths. On silica, we know that it doesn't absorb here, but somewhere in between, there's a cutoff between these two charge densities. And so we can also tune that with pH, and that's the end of the story at this point. So I've shown you that we can absorb DNA nanostructures in a site-selective way. It shows promise for integration into next-generation lithography. We use diamond-like carbon and TMS-modified silica. They're simple, robust platforms. Tuning the surface chemistry is extremely important, and we believe that electrokinetic charge density plays a big role here. So we're investigating more surfaces to sort of broaden this and expand for other surfaces that are of relevant to the semiconductor industry, silicon, for example. And we also are interested in other absorption techniques that allow active control and placement. So, and here's a great picture of IBM Almaden and folks to thank, and thanks for your attention.